Welcome back, guys. Now we go for the convex optimization problems. So, of course, we discussed a lot about linear optimization problems, and we saw some tools, some ways of solving those problems. And at the end, we've seen also the simplex algorithm to address those problems and solve them automatically, of course. At this point, we are ready to go for convex optimization problems. And in fact, support vector machines are based on, actually depends on a convex optimization problem. So that's why we go for this subject at this point. Okay? First of all, we've seen that we can graph constraints when need to solve like a linear optimization problem. And we can solve those problems manually or algorithmically using the simplex method. Now, in terms of convex optimization problems, we're going to deal with a particular scenario, a particular case in which our constraints, they are linear constraints. We are going to start with convex constraints and linear objective function. This is one of those cases. By convex constraints, actually, I mean that we have a convex feasible set defined by our constraints. So this is a convex feasible region. As you can see, suppose that inside this region, we have a valid value for x1 and x2, of course, touching the boundary of the constraint as well. And consider we've got some linear objective function like this one. Of course, we can use the Lagrange multipliers as before. Lagrange multipliers are basically going to project those constraints or this single constraint into our surface, our linear surface, and then we're going to have solutions touching that projection. Of course, a maximum could be here and a minimum could be there, okay, at this point. And then using Lagrange multipliers, we're going to have all those critical points, and then we can assess if it is a minimum or a maximum, so we can decide what is our particular solution of interest. Okay? Just to recall the situation, just really fast, but nice to recall. Of course, we can use Lagrange multipliers, but in order to use Lagrange multipliers, first of all, we need to have a problem, this, which is, in this case, it is a linear objective function, as you guys can see here, just x plus y, subject to a convex constraint. It is convex, of course, this constraint, because if I get like any 2 points inside this feasible region, or of course touching the boundary, which is defined by the constraint itself, I can connect all those points using a line, and this affine function or line is going to be inside my space, my region. That's why it is a convex region formed by this particular constraint derived from the circle equation. You guys can notice. There are some conditions to use the Lagrange multipliers. First of all, my objective function f and my constraints must be differentiable. This is the case, yeah, I can differentiate. Does it consider one more equality constraints? Yes, it considers one equality constraint. I can use that equality constraint to solve my problem. Yes, I can. So, and the gradient of g is different of the zero vector. Yeah, of course, if I differentiate in terms of x, in terms of y, I will have 2x in terms of x and 2y in terms of y, so it's not the zero vector. So those are the basic constraints. At this point, I think you guys remember that the Lagrange multipliers are going to form a convex, are going to be used in a convex cone to define where the solution lies. That's most especially to make the quality constraints equal to the gradient of my quality constraints equal to the gradient of my objective function. I think you guys remember that, and it's really necessary, nice to go back if you don't. Just to remember, suppose this problem, a maximization in terms of x plus y, subject to this constraint, which is a convex constraint, forms actually convex region, sorry. So to solve the system, we basically do this. The gradient of f must be equal to the gradient of g, of my constraints, or constraint in this case, multiplied by some lambda. I think you guys remember, actually, this sign over here, it's not, in this case, it's not really necessary. It could be like without this sign, makes no difference. And of course, if it's a maximization problem, if I'm using the Karush-Tucker conditions, I can write this as the gradient of f, and on this side, minus lambda, the gradient of g equals 0. What is the same as the gradient of f equals plus lambda gradient of g. If I solve with minus here, I have the same candidate points and candidate solutions, and then I assess those points as we've seen before in previous videos. So now we solve this problem, okay, this system of equations, considering these gradients being parallel to each other, our constraint being equal to 0 must be satisfied. So in this case, the gradient of g of f is the derivation of this in terms of x is equal to 1, in terms of y is equal to 1, is here. And in differentiation of our constraint is going to be 2x and 2y. 2x and 2y multiplied by minus lambda, or as I mentioned before, it could be plus lambda. So I have this as my constraint, which is kept in my system of equations. I need to satisfy it. And then I'm going to have, of course, 1 equals to minus lambda 2x and 1 equals to minus lambda 2y, and my constraint equals 0. Okay? So solving for that, I think you guys remember that from previous videos. I can find the value for x and the value for y, plug it into my constraint, as in here, and finding values, possible values for lambda. So lambda can be minus or plus 1 over the square root of 2. So now I apply back lambdas over here to find my value of x and y, my values for x and y, which satisfy my system. So that was my next step, applying for lambda equals minus 1 over the square root of 2 and plus 1 over the square root of 2. So we found values for x and y, which ended up being the same, and x and y in this case, which ended up being the same as well. So now applying those two values, x, y, into my system, into my optimization function, my objective function. My objective function is going to provide square root of 2 and minus the square root of 2 as my two candidate solutions. If I look for a maximum for this x and this y, if I look for a minimum, I look for this x and this y. Okay? Solve, just ask you guys, solve without using this minus sign over here. You're gonna find the same solution. Okay? That's really nice to get in touch with Lagrange multipliers and understand what is happening behind the scenes. Okay? Okay, so that was our solution. We've got like a particular value x, y over here, a particular value x, y over there. And of course, my solution has to touch this, this constraint. I do not find any point inside my feasible region. It's always a point touched by my projection of the constraint. Okay? So that's a limitation of Lagrange multipliers. If I want to find some internal solution, as in this case we're going to see now, I need something else. So at this point, we're going to go for a different problem where constraints are linear and they form a convex feasible region. and my objective function is convex. It's not linear anymore, not just linear anymore. At this point, let's go just one more step. My objective function will be like this surface, okay, this parabolic surface. My solution, my minimum will be, of course, inside at this point over here, okay? Consider I'm looking for this minimum. This is actually the SVM optimization problem. If you take a look, my problem was like W power to 2. So of course, this is going to be a convex surface like this one, as you can see over here, okay? And my constraints are linear constraints in terms of something being greater than or equal to. In practice, you guys will see that linear constraints, all my linear constraints will form those linear functions you can see here as constraints, just as an illustration, of course. Okay. Actually, the region satisfying those constraints for SVM will be the internal region, which is a convex region. See, convex feasible region. Of course, I'm just imagining, of course, that I'm projecting the constraints into my surface in this picture. You can see that my solution does not touch, in this particular case, my constraints, but actually it is in the middle. So I need something else to solve this problem, which is not Lagrange multipliers. That's actually, it's not possible to solve with the simplex algorithm. It's not possible to solve with direct application of the Lagrange multipliers. I need something else. So just going back, okay, just to get back here. This is the primal problem for the support vector machine optimization. I think you guys remember. This is my convex optimization function. And those are my linear constraints, which I expect to form a feasible region. Of course, if I don't have a feasible region, at the end I'll have no solution because, I mean, constraints will try to enclose something, but one of the constraints will be completely outside of this definition of feasible region. Maybe my domain, solution domain, could be empty. That's my point over here, okay? So our primal solution, our primal optimization problem for the support vector machines is exactly this. This is how it looks like in this case, considering some x and some y in this case, okay? Of course, this x and y are not actually this y and this x over here, okay? This vector and this y over here. This is just like an axis for my system. We're going to understand how this looks like, our scenario, how we can see this convexity, how we can plot it. We're going to see that later. Don't worry for at this point. Just take a look here. I have something to the square. Of course, this is a dot product of w transposed w, square root of something to the square. When I apply this square to cancel out the square root, I'll have w transposed dot product w, which is the same as some function powered to 2. That's why I have a convex function, convex optimization function, objective function, as shown here. And those constraints are just illustrating one possibility. Just to imagine how those constraints, which are, of course, formally written here, cutting my space and define some internal region, visible region inside this space. Of course, if we solve this problem using Lagrange multipliers and make the appropriate substitution, we can actually find something that we discussed before, which is the dual form of my optimization problem. We did that before. You guys remember that if I find my dual, in this case, what's going to be the dual in this case? If this is a convex problem that I try to minimize, my dual will be a maximization, just the inverse. If this is convex, the dual will be concave. That means this is convex, like x squared, like x squared, and of course the concave will be the same as minus x squared. Okay? It will be a concave function, the mirror of this function, just the opposite of this function, the reflection of this function. And I expect my constraints to define as well some convex set, like here, visible convex region inside this place. Why it is important to be a convex region? Because I can just walk from one point to any other point inside, and which respects my constraints, that I don't cross to regions outside my feasible region. If I don't have a convex region over here, my algorithm needs to be really advanced in order to avoid crossing and leaving my feasible region to other nearby regions which do not contain any possible solution, in fact, because I wouldn't be accepting my constraints in that scenario. Okay, so in fact, what I need to find is actually I need to find points laying on the constraints when I try to solve some Lagrange multipliers, but in our case, I need to find some points, eventually points lying the constraints, if this minimum region over here would happen here, for example. But if it happens inside, I need to walk inside this feasible region and not actually solve for the equality as Lagrange multiplier does, which is the same as solving for any point touching my constraints, sorry, because we've got 4 in this plot. Actually, if we've got some minimum inside, I need to walk inside my feasible region. That's really nice, actually. So when I solve my problem, my primal problem looking for this minimum, what happens with my dual is that in the other space, in the dual space, which depends on completely different variables, I think you guys remember that, depends on other variables, I'll be finding some maximum, but not if this is a convex for the minimum, it's going to be a concave function for the maximum, just a mirror of this, okay? Just like minus x to the square. Okay, that's really nice. What happens now is we're going to see a method called interior point method, which is a way of solving, as the simplex is a way of solving linear problems, interior point methods are a way of solving problems when I need a solution inside my feasible region and not actually touching the constraint. Okay, so that's our next step. See you in the next video, guys.